Let's consider this phenomenon siphon. If the tube connecting the two reservoirs is full, then the liquid with a higher level of fluid empties into the tank with the liquid at lower level. How do we analyze this? To analyze this, let us consider the arrangement shown here. There's a liquid in the tank and there's a tube that runs from the tank, goes to a maximum height h3 above the datum and goes down to a distance h5 below the datum. There would definitely be a streamline, something like what we have shown here, 1, 2, 3, 4 and 5. Let us apply Bernoulli equation between the various points on these streamlines. This table organizes this determination. At point 1, on the surface of the liquid, on the free surface of the liquid in the tank, pressure head is clearly 0, the pressure being above the atmosphere, that is the gauge pressure, since the pressure at 1 is atmospheric. Clearly P1 is 0, P1 gauge is 0, so pressure head is 0. The elevation is 0 because we have taken the datum at that height. The velocity head is 0 because the velocity is negligible if the tank area is large, and the total head is 0 as in this row. Next we consider 5. Why 5? Because we know 2 of the 3 heads at 5. We know the pressure head to be 0 because the pressure at the exit is also atmospheric. We know the elevation head, which is minus h5 now, and since the total head must be 0 as required by the Bernoulli equation, we can determine the velocity head. And the velocity head simply would be what? h5 plus h5, because the elevation head is h5 minus h5, the total head is 0, so the pressure head must be h5. So the velocity head must be h5. As long as point 5 is below point 1 and the siphon tube is running full, there would be a positive velocity at h5 downwards. Then we move on to point 2. What do we know here? We don't know the pressure, this is inside the pipe, but we know the elevation head, which is 0, and we know the velocity head. Why? Because mass balance between point 2 and 5 would give you the same mass flow rate, and if the area of the tube is constant, then the velocity must be same. So the velocity head at 2 would be same as velocity head at 5, and velocity head at 5 is h5, so velocity head at 2 is h5. The elevation head is 0, and since the total must be 0, this means the pressure must be minus h5. There would be a vacuum pressure at point 2. The pressure at point 2 would be less than atmospheric inside the pipe. Interesting. Then we go to point 3 at the top of the siphon tube. At this point, the total head by Bernoulli equation must still be 0. The velocity head must be same h5. All across the tube it is same. Velocity head is h5. The total head is 0. The elevation is h3 now. So calculating this is determined, the pressure head is determined as minus H3 minus H5 to make the total head 0. Let's try one more. Point 4 at the same level as point 1, the free surface in the tank. The elevation head is 0. The velocity is same. So velocity head is H5. The total head required is 0. So this means the pressure head should be minus H5. All right? We have been able to find pressures everywhere in this tube. The pressure is at point 2, the pressure is subatmospheric. As we go up the tube, the pressure decreases. The minimum pressure is at point 3. And then as we go down the other limb, the pressure increases and increases to 0 value at the exit of the tube at point 5. If you plot this, let us take this to be the 0 line. The elevation head, point 1, 2 and 4 are at the datum, so the elevation head is 0 here. Point 3 is H3 above the datum, H3 above the datum, and point 5 is H5 below the datum, to the left in this diagram. The pressure heads we plot. The pressure at 1 is 0, and so is the pressure at point 5. Pressure 1, point 1 and point 5, both pressures are 0. Pressure at 3 is minimum, and pressure at 2 and 4 is minus V square by 2G. This is the velocity head minus V square by 2G everywhere throughout the pipe. Throughout the pipe, the velocity head is minus V square by 2G. This is also the piezometric head. Minus V square by 2G is a piezometric head. To this we add the velocity head to get the total energy head. And the piezometric head is minus V square by 2G. To this we add the velocity head of V square by 2G, and we get a total head of 0. So this is the total head throughout the tube. When would the siphon not work? You see, the lowest pressure is obtained at point 3. So the siphon would stop working when the pressure at point 3 is such that the water boils, that the cavitation occurs. And when would the cavitation occur? When the pressure becomes equal to or lower than the vapor pressure of water. So depending upon the temperature, the vapor pressure of water is quite low, a few kilopascals. So this sets the limit of when the siphon would work. If we neglect the small vapor pressure, then we may say the siphon would work till at point 3 there is total vacuum. The pressure becomes absolute 0. This means the height H3 plus H5 is equal to the barometric head, the atmospheric pressure converted into the liquid head. If liquid is water, then this is about 10 meters. So if the long arm of the siphon is about 10 meters, the siphon would not work. So we can empty a tank only if the long arm of the siphon is less than the barometric head, which is about 10 meters for water. Many of the flushing cisterns in your toilet work on the principle of siphon. There is a cistern that holds water because of a float valve, and there is a siphon tube that runs like this. The water level is maintained at a level up to here such that there is air on top at the siphon tube. Now, as you operate the handle, this big plunger is moved up. As it moves up, it displaces water inside this tube, and the water level rises and it completes the circuit. The water level rises and flows down, and once this tube flows full, it will not stop till all the water in the tank or the cistern is emptied. And so this results in a flush in the toilet. Let's consider another example, a little more complicated example of a natural draft in a chimney. Suppose we have a fireplace and a chimney to supply it air. And we let the natural draft do the supplying of air. How does it do it? Let's assume that the air flows across from 1 to 3 to 4 and then to 2. Point 1 is at the inlet of the chimney. Point 2 is at the outlet of a chimney. We can assume the velocity of A at point 1 to be nearly 0 because of large area. Let's assume the fire zone is a constant pressure fire zone in which the pressure does not change. So the velocity would be same, the air would be heated, the density would be lowered. Let's apply Bernoulli equation between point 4 and point 2. Point 4 just after the fire zone, and point 2 at the exit of the chimney of height h. The equation of Bernoulli would be V2 square by 2g plus P2 by rho g plus Z4 plus h should be equal to V4 square by 2g plus P4 by rho g plus Z4. Z4 is the elevation of point 4, which is 0 here. P4 is like P1, pressures are same, but pressure at P2, how do we obtain that? Now, let's assume that the gas is heated, the pressure is same, so the density would be lower. Let the density of gases within the chimney be rho, while the density of gases outside, the air outside, is rho naught. Pressure at 2 is determined from the external atmosphere. So pressure at 2 is P1 minus rho naught GH. Rho naught is the density of air in the atmosphere. Going up the height h, the pressure will reduce by rho naught GH. Rho naught is greater than rho. Then V4 is A2 V2 by A4. If we plug in the values in the Bernoulli equation, we get V2, the velocity at the exit of the chimney, to be this expression. Here you know the velocity depends directly as a square root of rho naught by rho minus 1. It only works if rho naught is more than rho. If rho naught is equal to rho, that is the temperature inside the chimney is the same as the temperature outside, so that rho naught is equal to rho, then this velocity would be 0. We also notice that the velocity varies like under root h, the height of the chimney. The more the height of the chimney, more is the velocity. A typical case is when A2 is much smaller than A4. The area at the fireplace is much more than the area at the exit of the chimney. So A2 by A4 is very small, so the denominator can be replaced by 1, and the velocity at the exit of the chimney is simply under root twice of rho naught by rho minus 1 times GH. Depending upon how much flow of air we want across the fireplace to keep the fire going, we can determine what should be the height of the chimney. This is an interesting example, a Heron's fountain, in which you see the water is being thrown above the level of water, the highest level of water contained within the tank. Why is this happening? From this tank, the water is flowing down into tank 3. Because of this water flowing down to 3, the pressure of air within 3 is increased. The pressure of air within the 3 is communicated to air at 2, and the increased pressure at 2 pushes the water up this tube, and the water can rise above the level of water in tank 1. A simple construction of Heron's fountain from used water bottles. Bernoulli equation can also be used to calculate the flow velocity in a pipe. Consider a liquid flowing through this. We use a bent tube aligned with the flow. In the lower end is aligned with the flow, and the upper end rises vertically. Because of the energy of the flow here, the water rises into this tube. This bent tube is known as the Pitot tube, after the French scientist who invented it. There is also a simple piezometer attached here to the wall of this tube, and the water rises in this tube to the height of piezometric height. Now, to calculate the velocity of the flow, assume a straight streamline between point 1 and 2. At U, the point 2, which is directly at the entrance of the bent Pitot tube, there is no flow taking place. So the velocity at point 2 is 0. And if we assume the velocity at point 1 is the velocity of the water flow, this velocity V or V1, then the Bernoulli equation gives you V2 square by 2G plus P2 by rho G plus Z2 is equal to same quantities with subscript 1. Here clearly Z1 is equal to Z2. The velocity at point 2 is 0, V2 is 0. So V1 is given by under root twice delta P by rho, where delta P is the pressure difference. By applying the hydrostatic rule, we can find out that P2 minus P1 is nothing but rho G times delta H, where delta H is the difference in level between the piezometric tube and the Pitot tube, so that the velocity at 1 is given as under root twice G delta H. This Pitot tube is used for velocity measurements very extensively. Almost all aircrafts measure their velocities through use of a properly designed Pitot tube. We will discuss more of this in later chapters. There are special names given to these pressures. P1 is named the static pressure. P2 is named the stagnation pressure, because this is the pressure where the flow has come to rest. The flow taking place along the streamline 1 to 2 has come to rest at point 2, is stagnating at point 2. So that's why P2 is termed as the stagnation pressure. And the difference P2 minus P1, which by Bernoulli equation is nothing but 1/2 rho V1 square, is termed as dynamic pressure, the pressure because of the velocity of the fluid. Dynamic pressure. Thank you very much.